Next, I'm very happy to welcome Professor Reza Moini from Princeton University. Despite his youthful appearance, he's one of the world experts on advances in cement-based materials, particularly with respect to additive manufacturing. And he's going to present resilience in architected materials by design as a means to harness sustainable infrastructure.
Thank you, Eric. I don't know if I'm an expert in anything, just a broad disclaimer, but thank you. Yeah, so let's see if this works. All right, perfect. Yeah, the title, it's a mouthful. So I'm going to talk about something a little exploratory today and something hopefully a little more applied. The more exploratory side of things is going to be architected material as it ties to additive manufacturing and things that are more applied. And then more applied thing is the additive manufacturing, although it probably is a little more exploratory for the times we live in. And I'm going to try to tell a story that addresses the resilience. There's a lot of talks about resilience, and it's related to sustainability. So hopefully by the end of this talk, I can kind of tie these four things together. Okay, so again, the title. Other than climate change, if I were to list all the other issues, although I have climate change on the title on this slide, rapid urbanization. All the issues of the future infrastructure. You have rapid urbanization on one side. By 2050, I was just looking at this data a few days ago for another reason. By 2050, there's going to be about another 2.2 billion people living in mostly urban areas. That translates to about 77 million people just in the US. On the other side, you have, so the cities have to grow. On the other side, you have, as everybody here is familiar, you have ASCE report cards. And for the most part, of course, there are categories when it comes to bridges and dams and structures, but for the most part, we're not doing so great. There has been a lot of interesting talks about composites today and innovative ways that everybody is working on that hopefully addresses this one. And more broadly, the World Meteorological Organization just published a report, I think a few months ago, that the likelihood of not meeting the 1.5 degree is from 0% that was in 2015 is up to 50-50. So we're really rolling a dice in the next few years. That means what does that mean for infrastructure? Well, that means we have to start, at least try to think about building structures that can last longer. There has been discussions about durability today. And resilience essentially can mean different things to different people. More broadly, it has a system level definition, but it can also have a structure definition, structural resiliency. It can also have a material definition in terms of coming up with materials that are more resilient. Of course, the National Academy of Engineering and United Nations have emphasized these in global context of human settlement and improvement in urban infrastructure. That, of course, as it ties to TIDC, that includes transportation systems. How do we go about resilient infrastructure? If you think about the fundamental, there was an earlier talk on the composites in the previous session. If you think about fundamental properties of material, strength, toughness, and stiffness, this comes with a trade-off, right? So the way we process the material affects the microstructure or the structure, and then that defines the properties and performances. When you come up with fiber reinforced concrete or polymer reinforced concrete, what we're changing is changing the microstructure. Therefore, you can control the properties and performance, and hopefully you can improve the durabilities. But that comes from the fact that we process the material in mostly conventional ways by casting, pultruding, or ways that are considered advanced manufacturing for the most part. But that's not the only way we can manufacture the structures. You can manufacture the structures through various ways, by laser processes, by additive manufacturing these days. And that means you can control this, not only the microstructure, you can control the sort of a mesostructure, where depending on your nozzle size, you can control the architecture of the structure. That enables another degree of freedom to control the properties and performances in the scales that are a little more applicable to infrastructure materials, and hopefully does not come at the cost of expensive advanced manufacturing processes. So back to this chart, there is a scale. So at this scale, you can change the way you process the material, change the microstructure, but civil infrastructure are here, right? In between, you have this architecture scale where you can change the way you arrange the material. Of course, you have to, again, have the processing in place. With that comes the definition of architected material, where you can define and design purposeful arrangements of material and therefore control their response. So what we do, for the most part, at least in my group, is for us, design comes from nature. We turn into nature. Nature offers abundant examples of resilient biological materials that can inform the design of hopefully resilient infrastructure. Of course, you have to have enabling manufacturing processes, and you have to understand the mechanics that informs these designs. And if you think about nature, so I'm going to do a quick transition to nature and back to more real context. If you think about nature, the building blocks of nature are basically either proteins on one side that are ductile and deformable, but not so strong. They don't have a high strength. On the other side, you have minerals. You have calcites, right? And aragonites that are that have high strength, but they're brittle. In between, of course, you have polysaccharides. So the more you move this way, you get stiffer, stronger material. The more you move back, you get tougher material, you get more ductility. So let's compare natural materials now in the context of the strength, stiffness, toughness with engineering materials. And of course, composite is going to be in this chart. So let's see where it is. Here's the trade-off, right? So engineering materials, you can increase the stiffness in this case, or the strength, by moving from essentially composite to ceramics. But of course, that comes on the y-axis. You have KIC, that's fracture toughness. That's, in other words, resistance to cracking, right? On the other side, you lose the ductility. You end up with a brittle response. Composites, of course, provide a nice trade-off, but on the other side, if you look at natural materials, you have calcite, those brittle minerals that I was talking about, and then on the other side, you have these ductile systems. In between, you have many biological materials that use clever, purposeful arrangements of proteins and calcite, but then they achieve good properties both with fracture toughness and stiffness, or with fracture toughness and strength. All right, so they're on the other side of the curve. And this is again done by using purposeful arrangements of the material. There are abundant examples. Nacre, for most of you probably know, but if you don't, mother of pearl. It's a shell, and it has a brick and mortar type of architecture, very different from the brick and mortar that we know in construction, but actually not far from achieving that in construction. And many other examples, chitons, mantis shrimp. So it has the fastest punch in the animal kingdom, and if you don't put it in a glass aquarium because it will break it for you, and so on. So there are many more examples, so I'm going to not really get into any of these details, but what happens here is that you, depending on, there are two ways you can design materials. One is that you would want impact resistant, you want ductility, or you want damage resistant. Depending on the property you want, you can go look for the right biological species, or you can be exploratory and find the right biological species that you're interested, and then try to understand the microstructure, but more importantly, the mechanisms with which the species survives and improves these trade-offs in material properties, right? For example, again, if you take the nacre example, it's you can increase the toughness that of otherwise brittle materials. So 95% of nacre is calcite. There's only 5% polymer in there. But by arranging them in such a brick and mortar fashion, you can get a fracture toughness that are 3,000 times higher than the calcite itself. And the examples are abundant. Here's another example of, so this is a coelacanth fish. It's actually extinct. These things are as old as dinosaurs in terms of how long it has taken for them to evolve. If you look at the fish scale, you have on one side, you have these, I marked it with blue. Over here, you have this twist in the arrangement of the fibers. So it's a interfibral bundle of fibers. So you have fibers and then you have interfibral matrix in between. For every orientation, there's a bilayer orientation. And it turns out that this layer essentially arrests the crack, where the other one makes it harder for the crack to propagate, because as you twist the crack, it's harder to shear a crack than to open a crack, if that makes any sense. So there are a variety of examples, variety of mechanisms that exist in this one. I just mentioned to crack arrest and crack twisting. But what happens is that if you, let's say, you can fabricate mortar or concrete structures out of this using additive manufacturing right here. Can you get any improved properties? It turns out that you can. So depending on your reference, this is your reference cast. If you just cast mortar in a mold and design your architecture informed by these systems, you can improve fracture toughness from 4 or 5 to 14, nearly 10 times higher, depending on where your reference is again. So these things are possible, and people are using additive manufacturing, advanced manufacturing to do this. So if I start thinking about what can you do to use these manufacturing processes to improve performances, you may ask, well, why additive manufacturing, right? So it's an enabling tool to make stronger material, but more broadly, why additive manufacturing? Because does everything need to be additively manufactured? There are 3 main aspects, right? So there is productivity, with automotive industry and aerospace industry, everything being automated using more efficient materials, but more efficient processes. I think Drew just made a great point about efficient designs and efficient technologies. So the reason the construction productivity has remained pretty flat for the past nearly 20 years is that we are not using any really automated processes in the system for the most part. And so what can these automated processes help us with? There is a debate between, doing a route, going down the route of prefabrication versus on-site. That depends on a variety of things. The other aspect that's related to this flat trend is automating the construction task. So, okay, so you can additively manufacture a house. You can maybe 3D print a bridge, which we don't know how it's going to respond because we're not there yet. But we're not also automating construction tasks, right? So automation in construction means many different things to people. Once you 3D print a house, you still need to automate the rest of the construction task. Have we ever seen a robot on a construction site? I doubt anybody has really seen it, unless you consider gantries and pavers as 3D printers. In that case, then yes. But if it comes to, especially in residential contexts, in terms of building cities that can accommodate more people faster, architects have done a lot of work in using robots to automate the task, but then deploying robots in construction sites are not necessarily a trivial thing. And so there's work to be done in this space, both academically and in the industry. The other aspect of using these automated manufacturing systems is that, well, the other technologies are coming, right? So, AIs and Internet of Things and robotics, they're coming, and they are more likely to participate in our society in ways that we don't anticipate as they grow and become more dominant. So there could be a synergistic effect that could be present in the future, which is why basically institutions, government agencies such as NSF are emphasizing thinking about these aspects. So what has happened in the additive manufacturing, when it transitioned a little more towards additive manufacturing, is that there has been a surge since 1994, where the first, since the inception of concrete 3D printing by Dr. Khoshnevis, there has been quite a lot of academic research, but there also has been a lot of adoption in the industry from startups and national labs and agencies. However, there is, as much as people say that the construction industry is not a very progressive industry, this is a very odd case because we are today in the US, we are 3D printing walls of the houses that are being permitted and are being sold. However, from a research perspective, we have very little knowledge about how these structures would respond and behave. How are these structures being built? Of course, those are more of a design build projects as opposed to being permitted on a regular basis, similar to other timber structures. And so we have the opportunity to think about better ways to design these structures that are already being built. And the reason this is being adopted is that there is financial interest in terms of cost saving, improving the productivity and transportation costs, which is basically, these are the drivers of adoption at the moment. Would this be long-term adopted or not? This is a test to be conducted in the next 5-6 years. Again, back to automating the construction task, additive manufacturing is only one piece of the puzzle, right? So you have the foundation, you have the raw house, so maybe you can 3D print this structures, but then the rest of the construction tasks are not automated, especially if you're thinking about additive manufacturing on site. And if you're thinking prefab, then there's the aspect of transportation. So what are the key aspects? If we get into a little more of the details, how is it done? Well, you have to have a processing platform that is specific, right? It's not a plug and play. You have to have the relevant skills, the relevant materials, the relevant integration systems. And you have to develop your own material that are conducive to the process that you have adopted. Then you have to think about how you design them, how do you program them, because these are layered by layer processes. Then you have to think about, well, what are those parameters? And you have to think about, are they going to hold shape? You remove the formwork. Whether you are in civil infrastructure or renewable energy, you could probably save about 50% cost, given some of the analysis that has been done, and provide the design flexibility using these, because you have the freedom of design, which gives you the freedom of fabrication. But can you overcome the printability and shape stability? Then again, these microstructural aspects are quite different in these systems. You have heterogeneities from the layer by layer processes. So there's a lot of unknown, and then you have to still consider the mechanical performances. So there's a lot of unknowns, but one approach is to tap on the opportunities, which is thinking about new ways of designing, whether it's at the material scale or at the structural scale. While as a community, we try to overcome these challenges. So I'm going to talk a little more about the processing platforms, just so people have a little more idea. So it has been done across different scales. Initially, it started from smaller scales and national labs and universities, and into the component scales. Again, in universities and startups and so on. And later on, U.S. Army Corp and a few other startups have adopted it for fabricating larger structures. There has been also use of these structures. This is a 3D printed bridge in transportation systems. This is a 3D printed bridge in Madrid. And there are basically two-story housing that have 3D printed walls with essentially reinforcement in horizontal and vertical systems. So how is it done? Again, you either have a gantry configuration where you use a layer by layer process to deposit the material, or you have what's called D-shape. You have a powder bed onto which you deposit, either the water if you have mortar, if you have a dry mortar, or cement paste if you have just aggregates, right? The trade-off between these systems is that, well, this one you have to overcome the shape stability. You don't have to be worried about shape stability, but then you have to consider a lot of the post processes that has to happen and take out the support material that has been sitting there. And it's not a very clean process. The other path for the platforms is the robotic configuration. So you can have a robot, but you either, if you're taking it to the construction site, it needs to be a relatively mobile robot. The advantage of using the system is that you can move it around, but then there are only so many industrial robots that are mainly are developed for automotive industry they can use in construction. So on the other side, robots are more versatile and you can use them for various construction tasks, although that needs to be developed. There has been other systems that has been used in Europe with smart dynamic casting, where you move the formwork, you're still casting concrete, pouring concrete into a mold, but you move the mold in order to create shapes that are perhaps more architecturally conducive. And there are cable state configurations that Oak Ridge, I think Oak Ridge National Lab is working on. The extrusion systems also need to be considered, right? So this is only the robotic or the automotive side. You still need to integrate these with some type of continuous or semi-continuous mixing procedures to develop the system. So people have done quite a bit of work in these areas at the component or larger scale structures where you have, for example, here you have a gantry, this is TUE, and you connect that with a pump that extrudes a single material. There has been also a lot of development in terms of extruding multiple materials or accelerating the cement hydration right at the tip of the nozzle, so you can reduce a lot of the mixing energy and settlement time in the process to make it more efficient. This is a schematic of the D-shape printing, where you can have the aggregate and the binder, or you can have the aggregate, or you can have the aggregate and the activator. It has been used in the context of polymers. This is essentially the same process as in laser, selective laser melting and selective laser sintering. Where you, instead of depositing material, you just hit the bed with the laser and deposit new layers of powder every time you print. Back to the construction tasks. So there has been, again, a lot of efforts have been done to use robots to, say, put the fabric of rebars together, to assemble a timber truss together, etc. But those are more of an off-site, prefab sort of a setting, as opposed to on-site processes. At Princeton, we do a lot of our bio-inspired designs at the smaller scale because we can understand the response of the material. We then scale up to sort of a mortar level where we can use robot arms, and then we scale up to mono extrusion and two-component extrusion, where you can have a concrete accelerant controlling, if I can get this work again, where you can have a concrete accelerant right here, control the solidification rates of the concrete as you deposit. And of course, you can make taller and taller objects. With this system, the difference is that the difference compared to conventional fabrication is that you can, because additive manufacturing is a controlled process, a relatively controlled process, at least in the laboratory or prefab scales, there is so much you can do with introducing ways for making better material, for using sustainable binders, for solidifying materials that are otherwise more difficult to solidify. For example, in terms of carbonation, you can only carbonate through the concrete so much. But if you can carbonate the material in the process, then you can use these additive processes to improve the way the materials solidify and therefore help their adoption and overcome their adoption to barrier. You can also generate a lot of data, and so you can understand how does the material does the material behave, and how can you change the performance of the material for change something in the process to improve the performance. So we do a lot of work in terms of in situ controlling of the mix design and controlling the processing parameters, all to improve the material properties, but also to come up with better processing as well. So in summary, This is a relatively interdisciplinary field, and we can talk about education and outreach and awareness. The challenge is, I think, again, that the previous speaker talked about this a little more in more details. Civil engineers don't like to program robots. Again, there's a lot of chemistry. If you didn't know this, there's a lot of characterization. There's a lot of understanding of fundamental mechanics, of fundamental microstructure. We need to bring people from other fields that are excited, or to excite the current and the upcoming generation about these technologies. I teach a course in autonomous fabrication and robotics at Princeton, where I get the best questions I've ever had in any class, any limited class that I've taught so far. So people have these. We don't have to reinvent the wheel, right? A lot of these things, a lot of the automation aspects, a lot of the processing aspects has been done. We can learn from other industries and bring experts from mechanical engineers, electrical engineers to help us do better control, better do processing. The other aspect is scaling up. These processes are specific. Everybody today does their own thing. They develop their own material. They work with their own supplier. They deploy their own robot. They program their own thing. And there's not a lot of data sharing. So scaling up becomes difficult. Translating information from one scale to another becomes difficult. And of course, there are scientific challenges in terms of what happens when you scale up a component from a laboratory scale to a larger scale that I think we can discuss. The whole point of, to me, the whole point of additive manufacturing is not to do conventional construction. Unless you're really going to be cost competitive because of the removal of the formwork. That again still is not opportunistic way of thinking about the design. Concrete, for as long as we know it, it pretty much does not have a mechanism that prevents it from propagation of a crack other than crack bridging and the things that happens in typical concrete as a composite in terms of having aggregates. Concrete is a composite material in itself, but it only has so much toughening mechanism to prevent the crack. There is an opportunity for us to design a material without changing the composition. So the materials is still the same. Just by controlling the materials architecture, you can improve the response without adding a cost, but indeed by reducing the cost because you're removing the formwork. Challenges are endless. I briefly touched about it. Reinforcement, interfaces, the weak interfaces and the size effects. There are numerous. I can give you a whole other hour talk. Discussion we can discuss for several hours about the existing reinforcement strategies. But reinforcement, when we think about reinforcement, we're thinking about reinforcement in terms of conventional concrete, right? If you're changing something entirely different, then you can rethink your reinforcement strategies. And the list goes on in terms of challenges, but I think the opportunities are more exciting. I've been lucky to have a good group to work through some of these early works, and I do have to acknowledge my supporters. Since this is about sustainability and resilience, I hope I conveyed that it is possible to make stronger materials by design, by additive manufacturing. It is also possible to make material more functional because you can introduce multiple material into the system. You can engineer material that can better capture carbon. They can capture water in terms of flood mitigation. We do have a small project with Port Authority of New York, New Jersey, where we are looking into particle packing. So particle packing is another example of things that has been done, but are not, maybe it's time to look into it in more details. ACI has a few committees on aggregate packing and particle size optimization. Just by changing, for example, in this case, just by changing your particle size distribution, introducing intermediate aggregates, you can improve particle packing by quite a bit and help reduce the cement content by about 20%. We did this for Wisconsin DOT in 2015, 2016, and there was a lot of saving just using ordinary Portland cement concrete. There is more to be done in this area of packing and particle size distribution. There is ready-mix concrete industry, I think, is very well tuned with binary aggregates, but not necessarily very well tuned with using multiple sets of aggregates where, asphalt industry is. People in asphalt industry constantly use power curve 0.45, a variety of a variety of particle size distributions to reach the ideal packing degrees. Those can be revisited when it comes to sustainable concrete alongside with the additive technologies. I hope this was somewhat useful and looking forward to the rest of the discussion.